First thing I'd like to do is like to introduce Microsemi. You may not be too familiar with the name. In fact, Microsemi has been involved in synchronization for a long time, specifically the group that I work with in Ottawa, Canada. We've been involved in synchronization since the switch over from analog telephony service to digital telephony service. You might have known us better than at Mitel. That transitioned a little bit later on to Mitel Semiconductor, where we started to get involved with the transition from digital telephony to IP-based or packet-based telephony. In terms of our synchronization expertise in this particular area, we started with our deployments in terms of the semiconductor products in production about 2003, where we first were trying to target frequency synchronization using packet clock recovery over wide area networks for communication infrastructure. That's the type of stuff that would be run by Bell Canada and AT&T in their WAN. About 2009 or so, we had our first products that were released for phase synchronization using IEEE 1588. That was about 7 years ago. That takes us to today, where we started to get involved with the SMPTE work, which is undergoing the same transformation as the communication industry did, which was the replacement of a legacy technology, if I can call it that, in SDI, and moving the service over to an IP-based service. With that transition, you've lost the synchronization aspect because packet networks are asynchronous, and you're trying to use 1588 to provide that synchronization service that used to be natively available. Okay? And that's what this presentation is going to talk about. It's going to talk about ST2059.2 and how that can faithfully provide the synchronization across an asynchronous packet network. The agenda that I've got set up here, I'm going to talk for about 40 or 45 minutes. The agenda I've got set up here is an introduction to IEEE 1588. That's where we're going to spend a lot of the time. What is this technology? How does the technology work? What are the terms and uses of this technology? I'm going to do a brief introduction to the profile itself. There'll be some follow-on speakers that are going to go into a little bit more detail on the interoperability aspects. And I'm going to cover a few deployment scenarios that, as an operator of the technology, if you had a studio, if you had a TV station, the choices that you can make when you try to operate a network. Finally, I'm going to finish up with some equipment design. So if you are doing system equipment design and you want to incorporate packet-based synchronization, how would you do that? Let's start with PTP introduction. The first term I want to introduce you to is an ordinary clock. An ordinary clock can be either a master or it can be a slave. It's the same term we use, ordinary clock. So if we're going to start on the top left-hand side, in gray we have a source of time. Typically for a TV station or an enterprise or a building, that source of time is going to be GPS. You're going to have a GPS antenna on the roof. You're going to have an antenna cable. It's going to be distributed in your building to some kind of box that decodes the GPS information and has that source of time. What you want to do now is you want to take that source of time and you want to encode that somehow for distribution within your building. Or it could be a distribution within a wide area network as well if you're in the communication industry. To do that distribution, we use a clock called an ordinary clock, and we configure it to be a master or we configure it to be a server. Master and server we use interchangeably. We take that source of time, we encode it inside specialized packets, these are called PTP packets, and we distribute that across our network, either in a multicast environment or in a unicast environment, where it reaches the end application that needs this synchronization. There you'll find an ordinary clock that's configured as a master or configured as a client. That receives that packet information, it decodes it, and using synchronization algorithms recovers the original source of time to align itself to the master. So terms here that we've introduced: ordinary clock operating as a master and a server, and on the right-hand side, an ordinary clock operating as a slave or a client. If I move to the next slide, the next term I want to introduce is a boundary clock. A boundary clock serves two roles. It serves as a master or a slave to upstream network, and if it's a client or a slave to the upstream network, and it operates as a master or a server to the downstream network. Effectively, a boundary clock segregates a network into two sub-networks. Why would I want to use a boundary clock? I might want to use a boundary clock if there were two different operators in the network. I might want that to be the handoff or exchange point between these two service providers. I might want to use a boundary clock if my network is very large. If my network had, say, 10 unaware network elements between the master of time and the user of time, I could put one in the middle to segregate the network into two pieces, and thereby have a 5-piece hop network followed by a boundary clock followed by another 5-piece hop network. That might not seem like a very advantageous thing to do for the cost of installing a boundary clock, but in fact dividing a 10-hop network into two 5-hop segments makes the technical challenge of recovering the original clock much, much simpler. The other thing I can do is I can install a boundary clock, say for example in a building, maybe one per floor. So if I had my master source of time in the basement of the building, I could then have a boundary clock spine along each individual floor that distributes out the time to the slave elements which are located on various places on various floors. So a boundary clock serves the purpose of segregating the network into smaller chunks to make it more usable. The next clock I'm going to talk about is a transparent clock. A transparent clock itself is a bit of a misnomer. It is not, in fact, a clock. The purpose of a transparent clock is to make an individual switch or router network element invisible to timing. So it's as if the packet, when it goes in on one port and goes out on another port, it's as if that switch or IP router element did not exist. So it's to make itself invisible in the network. Transparent clocks typically need to be deployed only in full greenfield scenarios. That means full new installation of equipment, whereas before the ordinary clocks and boundary clocks that we talked about could be installed in brownfield scenarios where you already had existing equipment deployed. Following on the last one is a management node. Now that you have the synchronization service running over your packet network, you might want to manage it. You might want to, first of all, find out the status of the operation of the slave clocks which are recovering the time. Are they actually locked and synchronized to the network? What's the type of timestamp information that you can retrieve? What's the packet jitter that's being observed? Is there packet loss being observed on the synchronization flow? So the management node in IEEE 1588 is specialized to the configuration and control and supervision of the synchronization service alone. It's not there to synchronize to manage the video traffic or the data traffic that may be on the network. It's there specifically to manage the synchronization network elements. Typically, you might find that an operator might have a specialist in the area of synchronization because it is a little bit of a niche technology that might be interested in an individual screen display or an individual view focusing on synchronization, and a management node could fill that role. How does the synchronization work? So this is really the core of PTP. This is how 1588 operates. On the left-hand side, we saw in orange, we saw the master clock. That's the clock that's got the time of day. That's the clock that's co-located with the GPS receiver that has the official time of day. And it wants to distribute that out to the various network elements that might need that time of day as a slave. What it does is it takes that time of day information, and as it sends it out across the packet network, it inserts the time of day into that packet. That insertion of that time of day is in the form of a timestamp, and that timestamp is labeled as T1. Say, for example, today is April 12, 2016. When that packet leaves the equipment, it'll insert a timestamp that says, hey, the time today is April 12, 2016. The resolution of that timestamp is down to the nanosecond level, even sub-nanosecond level if you want that level of accuracy. It then sends that information across the network in a sync packet to the various slaves that might need that information. The slaves receive that information. When that packet comes into that Ethernet port, they say, hey, this is a timing packet. Let me see what my local time is. So they get their local time of day counter value, and they input it into the same packet. That's called T2 timestamp. That's their local time of day information. Now, initially, when those slaves power up, their local time is all zeros. That represents January 1, 1970. That's the UTC epoch, or for PTP anyways. It now has two pieces of information. It has the time at which the time at the server, and it has the time at the slave. What it does not know is how long that information took to get to the slave. If it was the server and the packet got delayed, it could have taken a day to get to the slave. So at this point, it has some information, but that information is not tremendously useful yet because it doesn't know how long it took that information to get to the slave. So what it does next is it sends its own packet back to the master. It says, okay, I'm going to send a packet back to the source. As that packet leaves my equipment, I'm going to insert a timestamp. That timestamp is going to be called T3. I'm going to send that back to the master. When the master receives this as a delay request message, when it receives it on its ingress Ethernet port, it's going to say, hey, this is a timing packet. Let me record the time of day of my local clock. It calls that T4. It then sends the T4 information back to the slave as a delay response message. At this point in time, the slave has four key pieces of information. The T1, the time at which a packet left the master. T2, the time at which it arrived at the slave. T3, the time that it left the slave. T4, the time it arrived back at the master. With these four pieces of information, I can use the bullet points on the left-hand side, the sub-bullet points. I can use those formulas to figure out what was the delay between the master and the slave, and what's the offset between the master and the slave. From these four pieces of information, using these formulas, the slave can now say, hey, I have now faithfully determined that it's April 12, 2016. I'm good to go. There is some assumption built in there. That's the last bullet point. There is an assumption built in there that the upstream and the downstream paths are symmetrical. If you tend to be in a more WAN environment where you might have kilometers worth of cable length, that assumption could be put to the test. If you're inside an enterprise or a building where the cable lengths are much shorter because they're constrained by the size of the building, that might hold very well. I'm not going to get into this. This is a takeaway slide, if you will. Certainly you can get a copy of these slide decks. My business cards are on the table over there. I can email you, no problem. This is just covering the difference between an end-to-end clock and a peer-to-peer clock. I'll skip this one for the sake of time. So if we take a look at what's the great thing about 1588, because I'm sure probably a lot of you are familiar with NTP. I mean, NTP's been around a long time. It does a job very well. Your computer probably gets the time from NTP. Up it comes, boom, I have NTP, I have the time. Why do I need something else? Why do I need something else besides NTP? The great thing about IEEE 1588 is it allows the concept of profiles. NTP is very powerful. There's one way to operate NTP, one universal way that everybody runs NTP. And that's not subject to change, and it's not subject to user modification. 1588 allowed this concept called profiles. It allowed industry organizations, or in fact users if you will, it allowed them to customize the protocol to select those parts which were most applicable to their industry, as well as to extend the protocol in ways that made sense for their industry. So it allowed this flexibility for groups like SMPTE to use a subset of the functions and exclude the functions it didn't want, and to extend some functionality that might be very applicable to them. For example, the daily jam. That sort of things are not really possible with NTP. The functionality is not embedded in there so that you can have that kind of control over the protocol. So that's the power of IEEE 1588. That's why a lot of industries have adopted it. Is it's got that flexibility built in to allow a user community of experts to modify it as they like. So let's talk about those industries that have adopted it. Certainly it's very new to SMPTE, I would say. I think the profile was released last year, 2015. That's only a year. Certainly, it can take time for a technology to be accepted in the industry. It can take time for people to feel very comfortable that the technology is robust. But let's take a look at some of the other industries that have used this technology. If we start in Microsemi's background, which is the communication industry, that's operators like AT&T and Verizon, Bell Canada, if you will, since we're up here in Canada. They've been deploying IEEE 1588 for many years now. The first profile that was released was focused on frequency synchronization. That was in 2010. So that's got 6 years of standardization and 6 years, maybe even a little bit more, of field deployments. If we move down a little bit, they've had since about 2014 phase synchronization, which is very applicable here. They have very similar targets to what you have. Their targets are 1.5 microseconds for phase alignment performance. Your targets here are 1 microsecond. Now, a little bit of difference with the ITU is that their targets are over a WAN environment. They're talking about 20 or 30 switch network elements that may be aware of 1588, may not be aware of 1588, getting 1.5 microseconds. The SMPTE challenge is typically much more stringent. You only have 2 or 3 elements between the master and the slave because you're typically in a building. And your performance requirements are 1 microsecond. So in fact, the communication industry has solved a much more difficult challenge a few years ago in a very elegant way. If we look at some of the other industries that have adopted it, cable as well. If you look at Rogers Communication, for example, Cox and Comcast, they have a similar problem. They used to have a native technology that was DOCSIS that used to carry the time natively. They've gotten rid of that. They've gone to IP Ethernet connectivity. They need to have synchronization for that. Some of the other ones, power industry, for example, had proprietary legacy. Let's call it legacy interfaces. For example, ERIC-B used to carry synchronization natively. Those are going away as you move to IP Ethernet. They too need to replace their synchronization capability. For the audio-video industry in general, I think there's a few standards bodies that are actually targeting that market. I think the core one, of course, is SMPTE here, the ST2059-2, which was released last year. But there are other associated profiles that may be relevant to some of you people in the room that are working on slightly adjacent industries. So for example, AES, looking at audio equipment, they have their own profile as well that's customized for their use case. And then the kind of a little bit more of an umbrella organization, the IEEE 802, which had something called audio video broadcasting, AVB, now renamed as time-sensitive networking, TSN. They also have a suite of protocols that are somewhat targeted for audio-video use case, either in the home or in the professional environment. So all of those might be relevant to you, to your work. just a brief introduction to equipment design, that the profile is only one piece of the solution. I think that's one of the points I want to hammer home today, that the profile itself, the PTP operation of PTP, is really only focusing on interoperability. And there's going to be some presentation material a little bit later on from Lee and company talking about interoperability. That's only one piece of the puzzle. It's one thing if I can send you timestamps and you can send me timestamps and we can communicate information. It's another game altogether to see if that information can be faithfully recovered to get 1 microsecond. That's a performance specification. It's another level of detail that needs to be added. Profile is the first step. I can talk to you, you can talk to me. Performance and architecting your network is an entirely different level of requirement specification. And I'm going to walk you through that in a little bit. So let's talk about 2059 just in brief. I won't go into a lot of this detail. This was primarily, I guess, more for me when I was first learning about the SMPTE organization, the committees and the groups and the standards that are being worked on. In green here is the focus for tonight, ST2059.2. But I think what I want to emphasize here is some of the engineering guidelines which are coming on stream. Profile is a great start, but some of these engineering guidelines that are being developed are going to be really important for the operation of the network. How many nodes can I deploy? What type of equipment can I buy? What is the performance I can achieve? What are the loading levels that I can have on my network? These engineering guidelines are going to be key to pull together a full deployment. So let's take a look at a little bit of details on the broadcast profile. It's using the default BMCA. That's fantastic. It's reusing what's already been done by the IEEE 1588 working group. The path delay is an interesting one. Path delay is available as both the default end-to-end as well as the peer-to-peer. It's good that you have the flexibility to do both end-to-end and peer-to-peer. One of the difficulties with that is interoperability. The end-to-end and the peer-to-peer are not interoperable. So that becomes the first challenge for an operator of this technology. If I was an operator, if I was CBC, for example, or if I was NBC and I wanted to deploy this technology, I would actually need to be somewhat of an expert in the SMPTE standard, ST2059.2, to identify that there are two subclasses of operational models, end-to-end and peer-to-peer, and to select the one that I wanted to have, and then to go out and purchase the equipment that was capable of the one that I have selected. Because it may not be that all the equipment design supports both. Of course, if you're on the other hand, if you're an equipment designer, it's important for you to include both because both are in the profile. So that's the first one I wanted to highlight. The packet rates are also interesting. You can see some of the packet rates are in log format, log base 2. Typically, I think the packet rate here that we would suggest would be about 8 packets per second, but maybe 1 packet per second is a little bit more interoperable. Again, packet rates are really focused a little bit more on interoperability. If you really want to squeeze the performance out of this, you need to look at your network architecture, the amount of packet jitter, the amount of switches and routers that are in your network to see what's the best packet rate for your deployment, and to configure your equipment with that packet rate. We see in the communication industry when we try and address Brownfield, where you might have 5 legacy switch routers or 10 legacy switch routers between your master and the slave, the packet rates are normally much faster, tend to be 64 packets per second, even 128 packets per second. Again, if you look on the right-hand side with the clocks, again, you can see that both end-to-end and peer-to-peer type clocks are allowed. Again, you need to, as an operator of the network, you'll need to make sure that you choose the one that's uniform throughout your domain, whereas if you're an equipment vendor, you might want to support both. The other parts that are very interesting are the transport layer. You can see that both IPv4 and IPv6 are permitted. It's actually very similar in the communication industry. Of course, one of those things about that is IPv4 and IPv6 are not interoperable. So again, as an operator of the equipment, you'll need to figure out which one you want to use for all of your equipment. And if you do want to have some parts of your network which are IPv4 based and some newer parts of your network which are IPv6 based, that's the perfect place to install a boundary clock. A boundary clock can terminate the IPv4 domain and convert it over to an IPv6 domain. That's the perfect application for a boundary clock to segregate those two domains. Thank you very much. Next up is the use of multicast and unicast. You can see there's some flexibility there again. Do I want to have a multicast deployment or a unicast deployment? Multicast is great. It reduces the load on the master because only one connection can be visible by many slaves. The downside of multicast, depending on the router switch equipment that you've installed, for example, Cisco tends to dominate the enterprise in terms of the switch routers which are installed in this building or in a TV station. They might tell you that multicast queues and the handling of multicast quality of service might result in different asymmetries upstream and downstream through the equipment. So it's one thing to take care with the use of multicast is, does it introduce asymmetries in the queuing of the switches going downstream and upstream, especially if downstream is multicasted and upstream is unicasted? Are you introducing different delays along those paths? Something to take care of. The performance target here is 1 microsecond, which is very reasonable for an enterprise, absolutely perfectly reasonable for an enterprise target. If we look at some of the lock time requirements, so for example, 5 slaves, one would say that's very aggressive. Looking at the communication industry where we have 5 or 10 unaware network elements, typically the synchronization time is on the order of minutes. It's not on the order of seconds. So that can be a little bit of a challenge for the deployment. Some of the other things that are permitted are alternate master, path trace, unicast negotiation, alternate timescales. Again, one of the things the profile does is it forces as an operator of the network, as a purchaser of the equipment and a configuration of the equipment, to make sure all the equipment selects the same mode of operation, otherwise they won't be able to talk to each other. So you've got some flexibility built in here to the profile, but that puts a burden on the operator to be a little bit more sophisticated, a little bit better understanding of the profile so they can select compatible requirements across their network. Certainly from a performance aspect, though, it's very reasonable to achieve 1 microsecond with this technology. Deployment scenarios. So if we can take a look at this, I stole this from somebody's document, perhaps somebody that's in the room. I don't know. Apologies if I did. But you can see just translated, first of all, in terms of deployment scenario, into terminology that might be more familiar to you before we switch over to the PTP clocks. We have the video source, which has legacy SDI interfaces, if I can call it that, going to encoders, which are translating that to IP, Ethernet connectivity, 10 gig, 40 gig, for example. Going across the network, arriving at the decoders, where again they're converted back to legacy SDI interfaces, almost like a circuit emulation, almost like a pseudowire type capability, where you have what you want on both sides, SDI carrying both synchronization as well as the video, and in between you've inserted an asynchronous packet network. So let's take a look at that in terms of PTP clocking. How does that work? So again, on the top left-hand side, we see that gray clock that I introduced on one of the earlier slides. It's your GNSS receiver. It's your GPS receiver that you might have in the building. That GPS receiver sends information to a ordinary clock master, which takes that GPS information, encodes it in packets, sends it across the network to the slave. This deployment looks great. This is for a brownfield. If I've already outfitted this particular building here at Ryerson, if I've already outfitted this building with existing IP switch routers, I don't necessarily want to change them. I might just want to install a master in the basement of the building, and I install a slave where I need that synchronization of time. It's great for the operator, this deployment. They don't have to change their installed equipment base that they've paid a lot of money for. The disadvantage of this is that the performance may be uncertain. The disadvantage is, as an operator of this network, I really need to make sure that the network is architectured according to the engineering guidelines to make sure that the traffic loading levels aren't too high, the number of hops between the master and the slave is not too great, and that the asymmetries between them is not too significant. I need to take care of any translation between different Ethernet speeds. If I have 10 gig Ethernet links, 40 gig Ethernet links, 1 gig Ethernet links, I need to take care of all those things to make sure that the service will work properly for me. So advantageous, it's going to be cheaper to deploy because I don't need to change the equipment that I have. Disadvantage is it may be unknown. If we look at the communication industry, this is the exact problem that they wanted to solve. You can understand that in a building, it might be simply easier to change out the equipment because it's all localized within this building. It's certainly a known, controlled problem. If I was in a WAN environment in AT&T and I had to cover an entire city, if I had to cover an entire state with infrastructure, certainly to go out to all the places where I have my equipment installed would be a bugger. So there, solving the brownfield challenge became critically important to them. So this is where the communication has a history of solving this particular problem to the 1 microsecond, 1.5 microsecond level. It is achievable if you have strong engineering guidelines in place to tell the operator how best to configure their equipment. It's not necessarily just saying, okay, turn on quality of service, away you go. There might need to be more detailed information on the engineering guidelines in order to achieve this. What we can do to help, though, is maybe we can install boundary clocks in strategic locations. Boundary clocks are great, for example, at entry points to stadiums. They're great at entry points to shopping malls, entry points to enterprises where you might have a handoff between a WAN environment and a LAN environment. And they might be very nice, again, on a per-floor basis in a building to have strong recovery of the clock per floor and then distribution within the floor to the slave clock. So I don't necessarily need to change out all the switch routers. It might be on people's desks, under people's desks, in cabinets and whatnot. But if I have a spine on the backplane of my enterprise, I can install boundary clocks there strategically without incurring too much cost in order to get more assured performance. It's a little bit of a compromise. If I had unlimited money, if I was from CBC, I don't know if anybody here from CBC, I had unlimited money from the government. through the generosity of the Canadian taxpayer, I could replace all of my IP routers and switches with new equipment that was boundary clock capable. If I did that, I could then have assured performance of my synchronization flow end to end. There is a profile covered in this in communication industry. So if you look at this particular deployment where I have all new greenfield boundary clocks installed, this is where you can see in the communication industry they have millions of nodes deployed, for example, in China as one example of this already with extremely high performance. 100 nanoseconds can be achieved with this type of deployment in a very certain, very assured, very comfortable way. Okay. The downside, of course, is you need to replace all that equipment that's already been installed with new equipment that's 1588 capable. Now, that could be just replacing the line card if it was a chassis system, or it could be replacing the entire node if it was a pizza box. It depends upon the equipment that you've purchased. Transparent clocks are another example of all new greenfield equipment. Here's another key slide. I'm going to spend a little bit more time on this, which is the budgeting exercise. It's great that we have a target of 1 microsecond. That's fantastic. Okay, 1 microsecond, that's what we need to achieve. How, as an operator of a network, if I own this building and I needed to get 1 microsecond to every user, how do I do that? How do I partition this 1 microsecond between the various sources of error that are in my building? So I'm going to take an example of having 10 hops between the master source of time and the slave source of time. So I'm going to have 10 boundary clocks installed here. The first budget I want to assign is to the GPS. My GPS might be on the antenna. I might have an antenna on my roof. I might have an indoor GPS. You know, if I had advanced indoor capability, I could have advanced indoor GPS. I'm going to want to budget error to that GPS receiver of 100 nanoseconds. This becomes important if I want to have the same synchronization across 2 buildings, for example, that have independent traceability to GPS. So I'm going to budget 100 nanoseconds of error just to GPS alone. Next thing I want to do is I want to start budgeting some error to the cables that I might have. Cables themselves, I'm thinking specifically of optical cables, where you have a transmission optical cable and you have a reception optical cables. They can be of different lengths. It tends to be, as an operator, when you install your cables, you spool them in case there's a cable break. So you might spool these cables in a cabinet, and of course your spooling is not regulated or controlled. The operator goes, he installs it, he spools how much, he puts it in the cabinet, and away he goes. So it could be that you have asymmetries in your cables. Now, in a WAN environment, of course, this might be a little bit larger budget. If it was a smaller building, smaller enterprise, of course, this could be a smaller budget. So here I've got 10 pairs of cables between my 10 boundary clocks. And I've got a budget, 11 of them, and I've got a budget of 10 nanoseconds for each pair. That gives me a total budgeting of 110 nanoseconds. Next thing I want to do is I want to budget some constant time error to the boundary clocks that I've installed. So each boundary clock is responsible to terminate the upstream connection and generate a new downstream connection. Inside that boundary clock, depending upon the equipment design, I've introduced some time error. I have buffers inside that equipment. Those buffers introduce input-output error. I have some traces to carry the clock and carry the 1 PPS inside that equipment. Those traces carry asymmetry time error. So I'm going to budget for those individual pieces of equipment, especially if they're chassis-based. I'm going to budget 50 nanoseconds of error inside the equipment design. I'm going to have 10 of those boundary clocks. That gives me a total of 500 nanoseconds allocated to the boundary clock, switch, router, network elements. This is something that you can give to if you're an operator of the network, this is something that you can give to your equipment supplier saying, how much error does your box introduce that's constant and fixed that you cannot remove? 50 could be a target that you could assign them. Dynamic noise. Dynamic noise tends to be the oscillator noise that's inside the boundary clock. All of these equipments have oscillators. Those oscillators have noise. Of course, you're filtering the incoming signal. That means you're allowing the high-pass noise to come through from the oscillator. That noise is going to be dynamic. So if we budget 50 nanoseconds of dynamic noise for each network element, we have 10 network elements, we come up with 158. How the math works on that is I take 50 and I multiply it by the square root of 10, and I get 158, because dynamic noise, we can assume some kind of RMS addition, some kind of square root of sum of squares. Okay, so we don't necessarily have to make that linearly, because that is dynamic noise. The end application itself, that's the video camera, that's the webcam, that's the decoder, that whoever needs to have that synchronization, we can assign that equipment 100 nanoseconds. Total, so if I add all these up, 100, 110, 500, 158, 100, I now have an end-to-end budget of 968 nanoseconds, which is below my 1 microsecond target. And now I'm in position to define each element that I need in my network. I'm going to go buy cables, or I'm going to go look at how I've had my cables run through my building. I know the budget that I need to concern myself with for the cable links or the asymmetry on the cable links. I'm going to go buy a GPS receiver. I'm going to go buy a grandmaster. I now know the budget I need to have from that grandmaster vendor. I'm going to go buy some switches and routers, which are boundary clocks or repeater clocks. I now know the type of specification I need to give to my equipment manufacturer so that I can plug all these things together so that the noise error won't accumulate beyond what I need. And now for the end application that uses it, I know how much budget is allocated to them. So now I can deploy a properly designed network with assurance of getting 1 microsecond. This is a very powerful slide in terms of engineering guidelines that you won't actually find in the ST2059-2 profile. Okay. But this is the budgeting exercise you will need to do as an operator to make this technology work. The last section here is looking at equipment design. So what type of equipment uses SMPTE profile? So for examples, it could be cameras, it could be microphones, it could be converters, encapsulators, de-encapsulators, encoders, decoders, and it could be the intermediate equipment that interconnects these, such as switches and routers that are in the enterprise. What would an equipment design look like? It would look something like this. So I'm going to look at the components inside the box. So this is really relevant for people who are designing equipment, the equipment system manufacturers. If I look on the left-hand side, I'm going to have some type of component in a PHY or in a switch that can timestamp packets. That might seem a little bit obvious, but that's necessary. That when a PTP packet goes in or out of my box, I need to be able to detect that it's a PTP packet, and I need to be able to timestamp it with some local time of day. I'm going to need to have some kind of software. That software is going to need to run the SMPTE profile in green there, or it's going to need to run the AES profile, or it needs to run the TSN AVB profile, or whichever profile is applicable for that particular deployment. I'm going to need in blue some kind of synchronization software that I can actually recover these timestamps, recreate the original frequency of the master, recreate the original phase of the master. And then I'm going to need some kind of system synchronization hardware that actually generates physical clocks that I can distribute in my box. It's going to generate the 27 meg, it's going to generate the 1 PPS, it's going to generate 125 meg, it's going to generate 48K, it's going to generate the physical clocks that are used by the various components. So let me walk you through a few flows. If you're designing a grandmaster, if you want to receive in GPS information and you want to fan that out into a building, if that's the system that you're trying to deploy, you're going to have a GPS receiver. It could be external GPS receiver. You can buy a dedicated system externally. That GPS receiver would normally give out a 1 PPS and it normally give out a time of day. That time of day might be NMEA format. It could be CCSA format. It could be ITU format. That's going to go into your hardware PLL. Your hardware PLL is going to lock to that 1 PPS signal, and it's going to fan that out to the various PTP components. Just looking at the synchronization here, it's going to fan that out to the various PTP components, typically as a clock, 125 meg, 25 meg, 156, 25 meg, and a 1 PPS. Those clocks and PPS are going to go to the time of day counters where you actually have the time of day. That time of day counter is going to be formatted typically 48-bit seconds, 32-bit nanoseconds. It's going to power up as all zeros, which is Jan 1, 1970. And that counter is going to increase based on the clock. In green, when I have a PTP packet to send, my profile says send a packet, says send 8 packets per second. The PTP engine is going to send that packet to your PHY. It's going to send it to your switch. It's going to send it to your FPGA, however you designed your system. When it goes through that timestamping unit is going to say, hey, this is a PTP packet. This isn't a video packet or a data packet or a voice packet. This is a PTP synchronization packet. I'm going to identify it based on the ether type or based on the UDP port number. I'm going to grab my local time of day counter value, going vertically downwards. I'm going to grab my local time of day counter value. I'm going to insert it. I'm going to send it on to the slave. The slave, likewise, when packets come in gray going left to right, it's going to come in. It's going to say, hey, this is a PTP packet that came from the slave. I'm going to go grab my time of day counter value. I'm going to insert it. I'm going to send it to the profile so the profile can properly terminate it. Here I've implemented a master. Next up, we have the boundary clocks and the slave clocks, which can be the same design. So on the left-hand side now, being a slave clock, let's just think about slave, less about boundary clocks. Packets are coming in from the master. They're going to reach my timestamping component. My timestamping component is going to say, hey, this is a PTP packet based on the ether type or based on UDP port number. It's going to grab the local time of day counter value. It's going to associate it with that packet. It's going to send the timestamp and the packet to the profile. The profile is going to terminate that packet. It's going to terminate the interoperability aspects, and it's going to extract out those timestamps. Those timestamps are going to be passed to some kind of synchronization algorithm. That synchronization algorithm is going to process those timestamps to recover the original frequency, recover the original phase. And then it's going to make a determination. It's going to say, hey, hardware, increase your frequency, decrease your frequency, increase your phase offset, decrease your phase offset. The hardware is then going to make those manipulations on the physical clock, 1588 clock and 15881 PPS, which goes to the counter value. The counter value is then going to be tuned with frequency and phase up and down, backwards and forwards, so that the next time a packet comes in, it's now being updated with a new counter value. We've got here a 3-component phase lock loop. Typically, phase lock loops that you're probably familiar with are all inside a single component. The timing loop is closed within a single IC. Here we've got a timing loop composed of the phase detector in the PHY, the linear filter in the software, and then the clock generation in an IC. You've got actually a large phase lock loop throughout your whole system. Even if that's a single board, if it's a chassis system, that could spread across multiple cards, because in a chassis system, your transport cards are going to be on the line, and then your synchronization control is going to be on your control cards. You can actually have a phase lock loop split across multiple cards, which is pretty cool, but can be a little bit challenging to design as well. Okay, so the pieces I want to take away from this are introduction to 1588 and some of the terminology that we use, ordinary clocks, boundary clocks specifically. The idea that the profile is fantastic, but as an operator of the profile, you need to make sure that you choose options which are interoperable with each other. And I think there'll be a follow-on presentation, if I'm not mistaken, that will focus on interoperability aspects. And then interoperability itself is not enough. You need to take it to the next level, which is budgeting the synchronization piece, that 1 microsecond, break it down into subcomponents to figure out the individual boxes and cables that you need to install in your building to make sure that the end application does have that 1 microsecond level performance. And finally, if you're an equipment designer, make sure that you're selecting the right components that have those type of functional modules inside of them to achieve the best result. My business card is on the bottom right-hand side there. I have them on the table. Feel free to come up and ask me any questions afterwards. I'd love to talk about IEEE 1588. I really enjoy the topic. If nothing else, I really appreciate your time today. Thank you.